And it's recording. Okay, so this is now part 4. And what I want to do here is I want to do an application of things related to the Fibonacci numbers to talk about roulette. So there's a lot of different ways of doing roulette. It would be really nice if we had a green marker, because then we could do the blacks, the reds. But because but because we don't have the green marker, we'll make things easier and we'll remove the greens from roulette and make it more advantageous for us. Vegas would never do this in practice. So the way roulette works is, you have your bunch of blacks, you have a bunch of reds, and then you spin, and then the ball ends up on either a black or a red. There's also two greens, 0 and double 0. And you can do many kinds of bets. We'll just do the simplest possible kind of bet. You bet on either red or black. And if you bet on red and it comes up red, you win. If you bet on red and it comes up black, you lose. Analogously on bets on black. And we will assume that if you bet $1 on red and it comes up red, you win $1. You also get your dollar back. Otherwise, it's really not good for you. And if you bet on red and it doesn't come up, then you lose your dollar. So here is a strategy guaranteed to make you millions.
Guaranteed.
Guaranteed. Now, of course, you may be wondering, if it's so guaranteed, why am I here and not in Vegas playing this right now?
You like teaching.
I love teaching so much. And the pizza in Vegas sucks. And they give you too much alcohol. So here's the strategy. It's called double plus one. Can't lose. So you start off, you bet $1 on red. If red, you win, and you're up $1. Else, if black, lose, and now you're down $1. So now what you do is you bet on red again. But now you bet $2 on red. If red, you win. And how much are you now up? You just won $2. Net, how much are you up? I'm sorry?
Well, did you lose the first? Or you
We lost the first.
Oh, you did lose. Oh, zero.
So we lost our first one, so we lost $1. Now we've just won 2, so we're now up net $1. Else, if black, we lose, and now how much are we down? So this is why it's double plus 1. So we keep doubling our bet. We bet $1, $2. Now we bet $4 on red. If red, we win, and we're now up how much? $1. If black, lose, and now how much are we down?
7.
Now we're down 7. And so it's called double plus 1 because you double your bet every single time, and the plus 1 is eventually you win $1. Now, this may not be that exciting, but instead of doing it as $1, do it as $100 or $1,000, or just follow the shampoo instructions, lather, rinse, repeat. Keep doing it again and again and again, and you can accumulate as much money as you want. So what is wrong with this strategy? So you lose significantly. So you might be at a point where, unfortunately, you have to put down $2.4 billion. And I think there was a conversation earlier over lunch as to how much money does the average Wellesley student carry in their wallets. Even in your ridiculous students' world, that would not be enough to put down a $2.4 billion bet. So what I'm going to do is I'm going to borrow something from economics, and I'm going to make a completely unreasonable assumption. The eccentric, now already I'm using my fingers. So the eccentric rich uncle aunt hypothesis. also known as, well, I'll just leave it like that. So you assume that you have a family member who has an incredible amount of wealth. So much so that if you need a $2.4 billion loan, they can do that. But they're eccentric. They won't just give you a dollar. They'll stake you for any amount you need, but they will not give you any money directly. So if you are worried about having to put down a bet of $2.4 billion, and if you then lose having to put down a bet of $4.8 billion, don't worry. Your eccentric rich aunt, uncle will help you out. So I don't want you to be concerned about whether or not you have $2.4 billion liquid. There's still something wrong with this, but if you don't know how roulette is actually done in the casinos, you won't realize the mistake.
Those green things.
I'm sorry?
Those green things.
So all the green things do is they change the likelihood of these events. So what we would do is, right now we assume we win with probability 1/2 and we lose with probability 1/2. When you add the greens, you have a slightly lower than 1/2 chance of winning and a slightly greater than 1/2 chance of losing. So what it means is it would just take you a little bit longer to net the $1. So the greens actually don't affect whether or not the method works. They just affect how long you have to do it. But you're getting closer because you need to know something about how roulette is done. So has anybody ever gambled large amounts of money that they want to admit to on roulette? So let's imagine you go to a table. We were already talking about whether or not you want to put down a $2.4 billion bet and whether or not you're able to. And we will make the unreasonable assumption that you always have the financial resources to do that. Do you think the casino wants to take a $2.4 billion bet? It's a huge risk for them. So it depends what you're betting on. You know, I think in the Patriots-Steelers game, the Browns are going to win. You're betting on the Browns to win against in Patriots-Steelers? Yes. Okay, we'll take that bet. Yeah. In a situation like that, Vegas will very happily take a bet. But if Vegas has a chance of losing a significant money, what they'll often do is they'll split the bet and cover themselves with some of the other casinos or other places so that no one is exposed too much. But at the tables, they have a lower limit and they have an upper limit as to how much you can bet. And so maybe the table, so this was one thing, and then you have table limits. Maybe this table is $1 to $50. That's not bad. That's a factor of 50 difference between the smallest bet and the largest bet. Well, let's see what happens if you start losing. You bet $1, $2, $4, $8, $16, $32, and then it's trouble. I started to write crap, but that would be bad because that's a different game. So here, you want to put down, you want to bet $64. Vegas is not letting you bet $64 on the table. They're capping the maximum bet at 50. So what happens is when you lose big, and then you reach the point where you can't put down the next bet. So what was the problem? We had 1, 2, 3, 4, 5, 6. We had 6 straight blacks to start off. And once we had 6 straight blacks, we lost a huge amount of money and we couldn't put down the next bet. So it all comes down to how likely is it that you'll have 6 straight blacks. And so we want to figure out what that probability is. So there's a couple of ways you can do this. Does anybody here teach statistics? Okay. What you could do is you could have students just simulate this. You play a bunch of games, and if you have the greens, then you'll have a slightly less than 1/2 chance. If not, you'll have a 50-50 chance. And then just see how often do you have 6 consecutive blacks. Gather some data and make a guess. You can also prove this using close cousins of the Fibonacci's. And so what I will do,
If you get the probability of 6 consecutive blacks, you do like 1 minus probability you don't get it.
yes,
Is that the easy way?
that's the easy way. I got to think for a second. Is that the way I want to do it? Yes, that's the way we want to do it. But then you have to figure out what's the probability you don't get it.
All right, so at least 1.
And that's anywhere in a string.
Yeah.
So for instance, imagine we do this a huge number of times. Say we do this 100 times. I have to make sure that nowhere in a string of 100 spins are there 6 consecutive blacks.
Oh, so you're finding like how many ways you can get.
So if you look at all strings of length 100 involving R for red and B for black, how often do you never have a run of 5 consecutive blacks? Or 6 consecutive blacks, or 7, whatever number we're doing. Now, you will...
Only like 94 ways to get 6 in a row or something?
I'm sorry?
There's only like...
Right. But then you have all the places you can fill in. And if you have 8 blacks in a row, this would actually count as several groups of 6. And so they're not all independent. So what I'll do is I will calculate the probability do not get 3 consecutive blacks. Hello.
Hi.
How are you doing?
I'm well. How are you?
Good.
Thank you for coming.
Oh, it's a pleasure to be here.
I brought sweets.
We're all gonna quit. Great. So we're all gonna quit in about 8 months.
So, do you know how to play roulette?
She's a statistic.
Oh, you're a statistics person. Excellent. Okay, do you know how to play roulette?
Yes.
Okay, so we're doing a simple version because they weren't able to give me a green marker. So Vegas is being generous today and has gotten rid of the 0 and the double 0.
Okay.
Do you know the strategy double plus 1?
No.
Okay, so you bet $1 on red. If it comes up red, you win $1. If not, you're down $1. Bet $2 on red. If it comes up red, you're up $1 net because you lost just won 2. If it comes up black, you're now down 3.
Okay.
Bet $4 on red. If it comes up red, you just won 4, you were down 3, you net 1.
Yep.
If not, you're down 7. So you always double your bet, and eventually you win $1. And then lather, rinse, repeat. You just keep doing this again and again and again, and you can make however much you want. Now, some people were a little bit concerned that you might have to put down a bet of $2.4 billion at one point. So we have introduced the eccentric rich uncle-aunt hypothesis, which posits the existence of a family member who will give you $2.4 billion if you need it for a bet, but will not just give you $1 directly. So you could place any bet you want. You have the financial resources to put the bet down. But the reason this is not enough is there's table limits. So just because you are willing to put down a bet does not mean Vegas is willing to take the bet. So for instance, imagine you start off with 6 straight blacks. So you lost $1, $2, $4, 8, 16, 32. Now you want to bet $64. Unfortunately, the table limit is 50. So when you lose big, and now you're really out of luck. And when you win small. So the question is, if you were to spin the wheel 100 times, what is the probability that at some point we have 6 consecutive blacks, or 7 consecutive blacks, or 8, whatever? And so one way you can do this is you can do this with statistics. You can write a computer program. You can assign what you want for the probability of winning. So we're doing 50-50, but you can add the greens. And then the students can just gather some data and make some conjectures. And they can plot as a function of both n and then the number of consecutives what those probabilities are. And this becomes then a great project in terms of two-dimensional visualization. Do you want to have snapshots for, this is the plot for 6 consecutive blacks, 7 consecutive blacks, 8 consecutive blacks? I'm going to show how you can calculate this theoretically using a generalization of the Fibonacci's. So in the interest of time, I'll just do the probability we do not get 3 consecutive blacks. If we can figure out the probability we don't get 3 consecutive blacks, it's not that hard to figure out the probability we do get 3 consecutive blacks. It's just 1 minus that. So we start here, and we have 2 possibilities. We get a black, and we get a red. And if you want, let's do the more general case. Let's say you have probability P of getting a red, and then probability 1 minus P of getting a black. And so what we will do is I will let AN be the probability do not have 3 consecutive blacks in n spins. Okay, so I want to calculate AN. And I know on my first spin I either get a red or a black. If my first spin is a red, what's the probability that I do not have 3 consecutive blacks and n spins, given that my first spin is red?
In the next spin?
No, from this point onward. So I have n minus 1 spins left to go. Given that my first spin is red, what's the probability that I do not have 3 consecutive blacks in the remaining spins? Not an. An is the probability I don't have 3 consecutive blacks in n spins. I've already done one spin. It's an minus 1. Right? Because the first spin is now gone. I have n minus 1 left. Now, my first spin here was a black. So now let's look at what happens on the next level. With probability p, I get a red. With probability 1 minus p, I get a black. And so what's the probability if my first 2 spins go black-red that I do not have 3 consecutive blacks in the n spins, the upgrade? It would be an minus 2. Oh, much better. Somebody must have won big and used this to get good markers. All right, so now let's do this again. And we have p, 1 minus p again. I'm beginning to run out of blackboard space, but I'll leave that for future Steve. OK, so now what's the probability if my first 3 spins go black, black, red, that I do not have 3 consecutive blacks? An minus 3. Do I need to worry about drawing more parts of the tree? No. I've got 3 blacks. Given that my first 3 spins were black, what is the probability I do not have 3 consecutive blacks anywhere in my n spins? 0. And that's why it's much easier to calculate, as was suggested, the probability we do not have 3 consecutive blacks, because the tree is now finite and ends. We have a recurrence relation. So this is very similar to the Fibonacci's we were doing before. So we get an OK, so these ones are now working. OK. I'm extremely paranoid in terms of how many things I actually travel with. OK, so we have, we did our little chart just in case some things didn't record. And with probability p, our first one was a red. With probability 1 minus p was a black. From this point onward, What's the probability we don't have 3 consecutive blacks? It's like we're playing the game, but with 1 fewer spins, so it's just a minus 1. It's somewhat similar in spirit to the memoryless process we did at the beginning today. Then if we had a black, then we could have a red or a black. This would be a n minus 2, red and black a n minus 3, and the advantage of doing 3 consecutive blacks is now this is just a 0. And so we get the recurrence relation. What's the probability we don't have 3 consecutive blacks in n spins? Well, it's p times this probability, which is a n minus 1, plus 1 minus p times a n minus 2, and then plus 1 minus p squared times p times a n minus 3. And so we now have a recurrence relation. This is very similar to the Fibonacci's. The difference is now it's length 3 rather than length 2. And instead of having the coefficients all be 1, the coefficients are now slightly different. And so any thoughts as to how we would solve this? This is one of the few times today where the mean value theorem will not work, because the mean value theorem is assuming continuity. And we have a discrete process here. But how did we solve the Fibonacci's? So one thing was creating the matrix allowed us to do the computation, but it didn't allow us to jump forward unless you know eigenvalues.
Can you multiply both sides by 1 minus p? Is it that or no?
Well, the problem is they have different indices.
Oh, yeah.
And so how did we solve the Fibonacci's? One was the method of divine inspiration. Induction won't work here. What did we guess was the solution? So you could just do the same thing. Oh, that blue is bad. So these will be the bad markers down here. So we could just guess an equals r to the n. And then when we go through, now we'll have a cubic equation to solve. And if you're doing 5, 6, 7, it gets worse and worse and worse. Unfortunately, there's no closed form expression for the roots of a quintic or higher. So you won't be able to write down a closed form expression like Binet. It's not horrible, because this is actually a fairly nice formula. We're not doing 10,000 spins. We're not going to go to Vegas that long. What we can do is, if we can just calculate the first few values, we can just march down with the recurrence. So let's try to calculate a couple of the values. What do you think is the probability we do not have 3 consecutive blacks if we spin no times? 1. What is the probability we have no set of 3 consecutive blacks if we only spin once? Also 1. The probability if we spin twice. If we spin 3 times. So it would be 1 minus, in this case, p cubed. I think. Was it? Oh, so 1 minus p cubed, sorry. So the only way to get 3 consecutive blacks would be black, black, black. Each one happens with probability 1 minus p. So the probability we don't have black, black, black would be 1 minus that. So we actually don't need a3. We actually only need these first 3 values. Because now I can use this recurrence. a3 is p times a2 plus 1 minus p a1 plus 1 minus p squared p times a0. I can calculate a3 from these. And if you put in 1, 1, 1, you should get 1 minus p cubed if you do the algebra. And so we can now use this and march down. So if you want to do Microsoft Excel, once you have 3 entries, the next entry is the weighted sum of the 3 above. So you can just march down with Excel, and you can calculate the probability. If we wanted to do 5, it would be a little bit higher. I think there's an 80% chance, I think, that you will have 5 consecutive blacks in 100 spins, if I remember correctly. The number is remarkably high. Vegas loves it when people come by wanting to do this, because they know that it will fail for most people. Could some people make money on this? Absolutely. But they'll make a small amount of money. So the amount of money they make on this when they win small. But the few people who lose, they lose big. It's actually also really good for Vegas for people to go home and say, I won, I beat the bank, to encourage more people to come. So there's a lot of great psychology that you can do. I remember a couple of years ago I was in the airport in Las Vegas, and they had the slot machines. but they weren't the slot machines I remembered from movies when I was a kid. For these ones, when you win, they don't shoot out the coins. You now have an electronic credit. Because if you have an electronic credit, you're more likely to keep playing, whereas if you have the money in hand, you're more likely to walk away. So there's a lot of really good psychology in terms of taking advantage of people's math ignorance. What they will also do is they will display the results of the last couple of spins. Because there are two types of morons. One type is, oh, red's come up 4 times in a row. Red is lucky. Let me bet on red. And then there's the other type of the morons, oh, red has come up 4 times in a row. Black is due. And they really don't care which type of moron you are, as long as you're one of the morons who will keep putting down money. So,
sorry guys, is Bella in here?
Yeah.
Can you come out here for a second? Sorry. The sub's telling kids to come find her. They want her in the hall of the test.
I just always worry when I'm talking about things with Vegas that they are so ever present that they will have me come to that little small room. So in terms of applications of Fibonacci's, we talked about real populations. Here's another one, trying to model a situation like this. How would you model something such as the likelihood of getting 4, 5, 6 consecutive reds or blacks? This is also really good for data integrity tests. If you have a string of 0s and 1s, what is your probability of getting a really large string? You can use this for some forensic analysis. And this is using just algebra. Now, if you want to solve this cubic, this is now higher mathematics. And this now becomes a little bit more painful. So, and if you wanted to get up to 5, 6, or 7, you will sadly no longer be able to do it in closed form. But for a lot of what you're doing, the closed form doesn't matter. The fact that we can now just march down, I think she had actually written the Excel program to just march down and see what the odds were. It's not that bad. So this is one of my favorite applications of cousins of the Fibonacci's. Any questions on this before? It's a shame it doesn't work. I remember my dad writing a program in BASIC when he heard about this. No, this can't be right. And just seeing how likely it was. So just people do not have a good intrinsic understanding of probabilities of rare events. And so the probability of starting off with 6 consecutive heads is quite unlikely. The probability that somewhere you have 6 consecutive heads is quite likely. It all comes down to, are you told where things are? The news is also a really good way of giving people false impressions. They don't report places where nothing happens. So I know there was, the report in 2008, Barack Obama and Hillary Clinton had exactly the same number of votes in some New York city. And there was about 12,000 votes. And people thought this was incredibly surprising. Well, if you actually calculate the probability and you look at how many places are voting in America, there should be a tie somewhere. The fact that the tie happened to be in this one place, that's unlikely. But they weren't saying ahead of time there was going to be a tie in this one place. Just that there should be a tie somewhere. And so we often do not have a good sense of unlikely events. Related to a lot of this is the idea of using statistics to get a sense of what the answer is. And just running some computer code, doing some analysis, getting a sense of the data. And so I'll go back and I'll do another divine inspiration. So today's the series sequence day. So power sums. I can't remember if we did this before. So let's say S1 of n is 1 plus 2 plus 3 plus n. S2 of n will be 1 squared plus 2 squared plus 3 squared plus n squared. And just in general, Sk of n will be 1 to the k plus 2 to the k plus n to the k. So the question is, what are the formulas for these? So these are often the standard things. So we sadly finished gambling. Did you do the calculation for the?
I was just doing it.
Yeah.
Almost there.
So we're shifting now to power sums. And just how would you estimate the sums of the first n integers or the first n squares or the first n kth powers? And so the first thing is when you have something like this, you want to get some rough estimate. So let's estimate, say, Sk of n. Can anybody give me an upper bound? And I don't care how bad the upper bound is.
2n squared.
I'm sorry? So here, instead of doing k, let's do the sum of the first powers. So 1 plus 2. Let's do an upper bound. What's the lot? N squared. Each term is at most n. So this is clearly going to be at most n squared. And for a lower bound, it's at most n. Drop everything down to 1. So the answer is somewhere between n and n squared. So unfortunately, this is not a good estimate because the range is too large. A lot of times, we actually don't care if it's n squared or 3n squared or 1/2 n squared. We just care how does it grow with n. Think of this as the runtime for a computer algorithm. What I care about is how is it going to scale as I change my parameter n. So the true value is much closer to n squared than n. So we want to get a better lower bound. So n is too bad of a lower bound. Any thoughts as to how we could do a better lower bound? So we replaced everything with 1, which was too excessive.
Balance it with switching within number 2.
So yes, let's start halfway. If we look at S1 of n, clearly that's going to be greater than or equal to n over 2 plus n over 2 plus 1 plus n. Just take the half of the values that are the largest. And this over here is basically n over 2 times n over 2, which is n squared over 4. I'm not worrying right now if n happens to be odd, But now we have n, 1/4 n squared is less than or equal to S1 of n is less than or equal to n squared. So we differ by a factor of 4, but we got the n squared, we got the independence correct. The independence is n squared. Another way to approximate this is to convert this to an integral. This is approximately integrating the function x from 1 to n. If I want to do sk, it's approximately integrating the function x to the k. And if I do that, I would get x to the k plus 1 over k plus 1. So it even gives me an idea of what I think that coefficient might be over there. But as a quick first input, it's not that bad to just look at this and say it's on the order of n squared. So there's two ways of proving these. One is you can be clever for S1, and then you can also use induction. So I'll show you the clever proof first. I'm sorry? The answer is triangle numbers, yes. But the question is, how do you see that it's the triangle numbers?
If you draw the triangular numbers, then you can double it, make a rectangle.
Okay, so one thing is, if you know how to write it like this is the geometric proof. And now if I double it, so I'm going to write everything twice. And I'll do the other ones with blue circles. 1, 2, 3, 4. 1, 2, 3, 1, 2, 1. So S4 plus S4 is going to give me this whole square where I double count the diagonal. So this would equal 4 squared minus 4. Oh, I'm sorry, I'm calling this S1. Sorry. So S1 of 4 plus S1 of 4 would be 4 squared minus 4. So in general, if I did it with n dots, S1 of n plus S1 of n would be n squared minus n. Or is it plus? It's plus, I'm sorry. I'm counting the diagonal twice.
And if you pushed it up so it wasn't a square, but it was a...
Oh, like a rectangle?
Then you can see it's...
Then it's n times n plus 1.
Yeah, to me that's easier.
Okay, right. Okay, so the other way you could do it is 1, 2, 3, 4, 1, 2, 3, 1, 2, 1. And then we put the other one coming up over here. 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. And so now you have a rectangle that's n by n plus 1. Here I have a square that's n by n, and I count the diagonal twice. And so I would just divide by 2, and I would get S1 of n is n squared plus n over 2, or n plus 1 over 2. And there's the area of the rectangle divided by 2. So this is the geometric proof. And for some of these, you can prove them geometrically. This one also has a nice alternate trick. And they often tell the story of how when Gauss was 5, the teacher wanted the little brats to just stop bothering so that they could just relax a little bit, and had them add up all the numbers from 1 to 100. And the other way of doing the problem is to notice, well, S1 of n is 1 plus 2 plus n minus 1 plus n. Let's write it again, but let's write it in reverse order. N plus n minus 1 plus 2 plus 1. And now when you add, you get twice S1 of n is n plus 1 plus n plus 1 plus n plus 1 plus n plus 1. So in each case, I'm always getting n plus 1, and I have it n times. And so you get S1 of n is n plus 1 over 2. So not surprisingly, we get the same answer again, which is nice. But the question is, well, what if we didn't see this? Yes?
No, so your first estimate, the lower and upper estimate, this is the average of those two things.
So in this, in the 1/4 n and the n squared?
So n squared plus n squared was our upper estimate.
Oh, I see.
The lower estimate, and then the average of the upper
Yes.
estimate is the true sum.
Yes. That's interesting. I have not seen that before. I think that's a fluke.
Okay.
But we should look at the next one and see if that works.
I just looked at the alert.
No, and it's interesting as to how you should average those two, because they're such different orders of magnitude. That in some sense, the lower bound estimate is garbage, because it's so much smaller than the n squared. And so for the higher stuff, I don't think it would work. But it's a nice observation. I've not seen that before. I think that's a result of low numbers. What you sometimes want to do is you almost want to do like a geometric average. But the problem here is when they have such different orders of magnitude, in some sense, one of the estimates is just garbage. And we are in the situation where one of the estimates is garbage. The way they often prove this is they prove it by induction. And so you guess a formula like this, and then you try to show that it holds. And so the problem with this is you need to know what the formula is.
Is that how they find some of these, by just guessing and
No.
Oh, okay.
And so there's advanced techniques that will tell you what polynomial to use. But what you can also do is, if you think that there's a polynomial, let's say we think that there's a polynomial. So I have S4. So this is going to be 1 to the 4th plus 2 to the 4th plus n to the 4th. If it's a polynomial, what degree do you think the polynomial is? Well, what's our upper bound for this? Not n to the 4th. N to the 5th. We replace each summand by n to the 4th. So this is going to be at most n to the 5th. And if we go just from the halfway point, we would have n halves to the 4th. So if we just go from n halves to the 4th plus n to the 4th, each one of these is at least n to the 4th over 16. So we would get n halves times n to the 4th over 16 is less than equal to S4 of n is less than equal to n to the 5th. So if we do that, we see the true order of magnitude of the sum is of size n to the 5th, but we don't know the constant. It's somewhere between 1/32 and 1. But what we could do is we could guess that S4 of n is some polynomial in n to the 5th. So maybe it's C5 n to the 5th plus C4 n to the 4th plus C3 n squared plus C2 n plus, n cubed, n squared plus C1n plus C0. If you do a little bit of work, you can see that C0 probably has to be 0. Because I could set all these sums at 0, and if I have no terms, when n equals 0, I should get 0. So with a little bit of work, we can see, well, if there's going to be anything, C0 has to be 0. But now I have a polynomial with 5 unknown coefficients. Well, what I can do is I can calculate the first 5 choices of n. Take n equals 1, 2, 3, 4, 5. And now figure out, this is now a system of 5 equations and 5 unknowns. And I can then figure out what the c's are. So take n in the set 1, 2, 3, 4, 5. Now we have 5 equations, 5 unknowns. And we can use that to now find the c's. And once we have the c's, now we can figure out what the answer is. We now then just proceed and prove it by induction. So let me do one of them by induction. I'll do, most people do the squares, so I'll do the cubes. The cubes is fun. So I will place the 1 with a 3. So let's figure out what this is. 1 cubed plus 2 cubed, 3 cubed, n cubed. And I claim, I'm really hoping I get this right, that S3 of n, and the reason I'm doing this is because of your nice comment, is this is one that looks really strange but happens to, is, I believe, n squared, n plus 1 squared over 4, which you might recognize as n plus 1 over 2 squared. So let's check. So base case, when n equals 1, does 1 cubed equal 1 times 2 over 2 squared? Yes. We don't need to, but let's check n equals 2. So we have 1 cubed plus 2 cubed, which is 9. Does that equal 2 times 3 over 2 squared? Yes. So I feel a little bit more confident about this because it's worked for 2 different places. So now let's prove it by induction. So inductive step. Assume true for n, show true for n plus 1. And everybody has seen induction before? All right, after this, I will prove everybody has the same name. I need at least one volunteer. Excellent, thank you. So I will prove everybody's name Jill. Okay, so which Jill said that? Okay, so we'll assume it's true for n, so it's true for n plus 1. So let's look at S3 of n plus 1. That's 1 cubed plus 2 cubed plus dot 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 plus n cubed plus n plus 1 cubed. Well, we're assuming the result holds for n. So by induction, we know what this is, right? By induction, this is just equal to n squared, n plus 1 squared over 4. And now we add n plus 1 cubed. Well, they both have an n plus 1 squared, so I can pull out an n plus 1 squared. And I'm left with n squared over 4 plus n plus 1. Well, let me have this have the same denominator, so I'll multiply by 4 over 4. So I'll get n squared plus 4n plus 4 over 4. Can anybody factor n squared plus 4n plus 4? It's n plus 2. So I now get n plus 1, and I'm going to write the n plus 2 in the pedantic way of n plus 1 over 4. And then each of these was squared, because this is really n plus 2 squared. And so this proves the inductive step. So the sum of the cubes is n plus 1 squared, n plus 1 squared over 4. There's a formula for all of them. Every single one is a polynomial. And you can always find the polynomial. Because it's a polynomial, if you just do the first few couple of values, you can then use your linear algebra to find the coefficients. And then once you have that, then you can do the induction. Notice that this would have been much harder if I didn't tell you what we were trying to prove, because then we wouldn't know what to put in here. So you'd have to do some work first. All right, so I'm going to prove everybody is now named Jill. Do you have any documentation on you that will prove that your name is Jill? A driver's license, a credit card? Okay, can you take it out? Are we willing to accept that? Well, wait, it does say this on your desk.
That is true.
Okay.
There's proof.
There's proof, right. Okay. All right, so we will accept this as proof that you are named Jill.
And on that.
It's in a different font. So everyone has the same name. And you might remember earlier today I was actually talking about how somebody else has my name and got into trouble for misusing mathematics. All right, so here is the statement. Pn in any set of n people all have the same name. Do you agree that if I can prove that this is true, then I will prove that everybody has the same name? I'm going to do this, in any set of n people, everybody always has the same name. So proof by induction. Base case. Is P1 true? If I give you a set with just one person in it, does everybody in that set have the same name? You all agree? Okay. So P1 is true. Hello, Jill. I'm sorry, I'm jumping the gun. So now let's do the inductive step. So we assume Pn is true, must show Pn plus 1 is true. Okay. This is where I wish I had my daughter who draws better than me, but all right, so I've got a bunch of people. All right. I'm assuming that whenever I have n people, they have the same name. So here's n plus 1 people. 1, 2, 3, ... n minus 1, and n plus 1. Okay? Let's look at the first n people. By the inductive assumption, they all have the same name. Right? All same name. Let's look at the last n people. All same name. But person 2 is in both groups. So everybody in the first set, they all have the same name. It's the same name as person 2. Everybody in the last n have the same name. It's the same as person 2. Therefore, they all have the same name. What's wrong? It's okay. We had enough Jills in here, So the statement Pn is that in any group with n people, all have the same name. We're trying to prove that. If we just have a group with one person, it's trivially true. There's only one person, so everybody in the group has the same name. Let's assume Pn is true. We have to show Pn plus 1 is true. So we assume in any set of n people, everybody has the same name. Let's look at n plus 1 people. The first n all have the same name. The last n all have the same name. And because person 2 is in both groups, everybody has the same name as person 2. So everybody is named Jill. Because we know at least one person in the world is named Jill. What is wrong with this? Is everybody named Jill? Should be. So what's going on? What's the mistake?
So what we're saying is true for numbers. The next one isn't true for the label numbers. So our proof by induction is always saying that these things are true because they'll work out algebraically to be the same.
Well, but I mean, I have my n plus 1 people. The first n people all have the same name. The last n all have the same name. Person 2 is in both groups. Do you see the mistake? Or
But person 3 is also in both.
yes, that's fine.
When you say Pn is true, you're saying it's true for a specific group.
No, but I was very careful when I said, in any set of n people, all have the same name. I'm not saying two different sets of n people have the same name. I'm saying whenever n people get together, it turns out they always have the same name. So if I can assume this is true, I'm able to show Pn plus 1 is true. So the way induction works is induction works like a ladder. And so you start off with the statement P0, and then you show that P0 implies P1. Now you can deduce P1 is true. And then you have P1 implies P2. Therefore, P2 is true. And you keep marching down. So what I did here is I did something subtly wrong. I drew a picture. And in the picture, I am assuming n is a big number, like 3. We have to show that whenever Pn is true, Pn plus 1 is true. If n equals 5, then yes, if P5 is true, P6 is true. If n equals 4, then yes, if P4 is true, then P2 is true. What if we only have P1 is true? Imagine n equals 1. Is P2 true? Well, if n equals 1, here is my initial person, person 1. Here is my next person, person 2. Here is my first group of n people. Here is my second group of n people. Is there anybody in common? No. So because there's no one in common, it breaks down.
So you skipped like from the first step
I did.
to the fifth step or something.
So basically, there's a missing step. From this point onward, it's correct. And so there's a lot of different ways you can do this. One way that people often phrase this is you prove all horses have the same color. And now you can prove anything in mathematics, because if this were not true, that would be a horse of a different color, which doesn't exist by the previous theorem. You can prove every integer is a perfect square. So there's a lot of different false proofs you can do on this. And it all comes down to you assuming something holds at the level of 2. Do you want to see that every integer is a square?
Yes.
Okay, so I will prove every integer is a square. Let me just double check how to do this. Okay, so Pn is the statement that any sum of n squares is a square. So I'm going to prove any sum of n squares is a square. And if I can prove this, then every number is a square. Because if this is the case, give me a number like 7, I can write 7 as 1 squared plus 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 1 squared, 2, 4, 6, plus 1 squared, which would then be some number squared. So if I can show any sum of n squares is a square, then every single number is a square, because I can just write it as a sum of 1 squareds. All right. Is P1 true, the base case? If I have a square, is it a square? Yes. So now we have to do the inductive step. Assume Pn, prove Pn plus 1. So imagine I have x1 squared plus x2 squared plus xn squared plus xn minus xn plus 1 squared. By induction, what's the sum of two squares? It's a square. So this would then be x1 squared plus x2 squared plus xn minus 1 squared. And now let's just call that x squared. But this is now just n terms. So by induction, this is a square. What went wrong? It should be a very similar mistake to proving that everybody's named Jill.
So you skipped the second step, right? 'Cause
I'm sorry. I'm sorry, Jill. What?
So a similar idea.
It's a similar idea.
1 squared plus 1 squared. So each particular person, yes, in their own data set is true, but 1 squared plus 1 squared does not equal 1 squared.
Correct. So we do not know that P2 is true. Here we're using P2, and here we're using Pn. We're assuming Pn is true, but it might be the case n equals 1. And if n equals 1, we don't know that P2 is true. I'm trying to mislead you by drawing a large sum. We don't necessarily know that we can do this. So it's really easy to subtly assume something and not even be aware that you're assuming it. And so the problem here is we are missing one step. If we had that step, then we would have all of this other stuff. There's a whole slew of proofs like this where if you start off with one false fact, boy, can you prove a lot of things. But sadly, none of these are available. Okay. So I wanted to shift to one last thing for sums. I just wanted to do a little bit of number theory. I just end the day on a little bit of a lighter note. So I was going to do just what the Riemann Zeta-Function is and some local global stuff to connect this to what we did before. And then I'll end with two very strange sequences. And they have some of my favorite quotes in all of mathematics. People have been banging their heads for years on some of these. Okay. So out of curiosity, has anybody here seen the Riemann Zeta-Function before? Okay. So these lectures were carefully planned over an extended 3-week period with everything perfectly fitting up and connecting to lead to this. So the Riemann Zeta-Function. And the goal is to actually go back to what we were doing early in the morning and see connections of the geometric series, see connections of this local global. So it's defined as zeta of s, and typically s is a complex variable. It's defined as the sum, n goes from 1 to infinity, of 1 over n to the s. And it turns out it also equals the product over p ranging over all the primes of 1 minus 1 over p to the s. Let me try to write s a little bit better. 1 over p to the s inverse. At least if the real part of s is greater than 1. If you don't want to think about s as a complex variable, you can think of just s as a real variable. S is positive in at least 1. And so the sum converges. And amazingly, the sum is the same as the product. So the first thing is, why is the sum equal to the product? So it's the fundamental theorem of arithmetic. So if you go back and listen to the video, I did promise we would do at least 2 fundamental theorems today. You have to do a lot to be denoted a fundamental theorem. So the fundamental theorem of arithmetic says every number can be written uniquely as a product of primes if you write the primes in increasing order. In particular, a certain number cannot be considered as prime. So what number cannot be prime? No, 2 is a prime. 1. Because if 1 were a prime, I could multiply by a number by 1 to the 5th, or 1 to the 8th, or 1 to the 10th, and I would no longer have a unique decomposition. So we do not consider 1 prime. 1 is also not considered composite. 1 is neither prime nor composite. It's considered a unit. So fundamental theorem of arithmetic, every integer greater or equal to 2 can be written uniquely as a product of primes in increasing order. And the reason I'm saying it like this is I don't want to consider 2 times 3 and 3 times 2 as different ways of writing the number 6. Let's just order them nicely. So I'll sketch why this is true. So let's look at 1 minus 1 over p. I'll use x rather than x, so I'll use a real number, x inverse. Well, another way of writing this is 1 over 1 minus 1 over p to the x. If I write it like this, does this remind you of anything? The geometric series. When you look at it like this, does this remind you of the geometric series? No. How you write mathematics really matters. So this is the same as 1 plus 1 over p to the x plus 1 over p to the 2x plus 1 over p to the 3x plus dot, 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 dot. So let me look at the product. I'm going to do all the primes up to some big prime, big P. And I have 1 minus 1 over p to the x inverse. So first I have all the 2's. 1 plus 1 over 2 to the x plus 1 over 2 to the 2x plus 1 over 2 to the 3x plus dot, dot, dot. Then I have the 3's. 1 plus 1 over 3 to the x plus 1 over 3 to the 2x plus dot, 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 all the way up to 1 plus 1 over big P to the x plus 1 over big P to the 2x plus dot, dot, dot. So I look at this product and I now multiply everything out. And so I have to take one term from this product, one term from this product, all the way down to one term from this product. I'm allowed to take one. So when you start looking at what numbers can you get, well, I can get the number 1. I just choose 1 every single time. I can get 2 to the x. I take 2 to the x here, and I take 1 every other time. I can get 1 over 3 to the x. I take 3 to the x here, and I take 1 every other time. Can I get 1 over 4 to the x? Yes. Take 1 over 2 to the x, and then take 1 every other time. Is there any other way to get 4x other than just taking this number? No, by unique factorization. Every integer can be written uniquely as a product of primes. So the only way I can do it is to have 2 twice. What about 5? Well, I would just get 5 from the 1 over 5 to the x. And now we finally come to our first interesting one. How do I get 1 over 6 to the x? One over 2 to the x and 1 over 3 to the x. So that's the only way I can get 1 over 6 to the x. What about 1 over 7 to the x? Well, we just take the prime from 1 over 7. Then we get 1 over 8 by taking the 2 cubed. 9, I would be taking 3 squared, the old phone company. 10, I would take 1 over 2 to the x and 1 over 5 to the x. Is that what Verizon is? Is Verizon what 9x became?
I don't think so. I think
Oh, they were different? I thought 9x became Verizon. Okay. I think so. So what you see is as I go through this, each number I will get once and only once. And I will get any number whose prime factorization uses only primes up to big P. And then this is where you have to do a little bit of analysis and make it a little bit more rigorous and just say that as you take more and more terms, you will capture every number. So clearly, when I look at this product, there's nothing in this product that's not in the sum of 1 over n to the s. But there might be terms here that aren't here. No, because if you have a term here, it has some factorization, and that will tell you exactly how far to go. So these two are the same. And this is one of the most useful functions to study number theory. So I'm going to give you an interesting problem. What is the closest prime number to 2017? So whenever you do math competitions, you have to know things about the number 2017. I'm sorry?
Yeah, you're right.
So 2017 is actually prime. So the closest prime to 2017 is itself. Okay? If I give you a number like 7, what's the next prime after 7? After 7. 11. After 11. After 13. Okay, so it's not so bad at the low values. At 2017, what's the next prime after 2017? Shh. Yeah. Okay. What's the next integer after 2017? And the next integer after 2018? Okay, so we understand the integers extremely well. There is really no mystery in the spacings between integers. And I actually even have an explicit formula for the location of the nth integer. Nth integer formula. Right? Not that hard. What about the nth prime? Where is the nth prime located? Are there infinitely many primes? And so the idea about this, it is not unreasonable to believe that this is a good function to look at because it involves primes, and if we want to study numbers, primes are the building blocks. They often talk about, chemistry, you've got your atoms, primes are atoms. This is a product over primes, so somehow primes are involved in this. This is good. Unfortunately, primes are very hard to understand. But this is very similar to all the stuff we did with generating functions. We somehow take this product, and when we take the product and put it together, we end up having a somewhat nice function over here. It's a sum over integers. We understand the integers. There is no mystery in the distribution of integers. So the idea is maybe we can use knowledge about the integers to get information about, the primes. So is there any value of s that you've seen before? 2. There's another value of s that you might have seen. 1. So if you take s equals 1, this is the harmonic series. So if you take s equals 1, this gives you the sum of 1 over n and goes from 1 to infinity. What do we know about the sum of the harmonics? It diverges. So I'm just wondering if no, it's still turning. Okay. Okay. So it diverges. So because it diverges, this is also equal to the product over p of 1 minus 1 over p inverse. This is the same as the product over primes. This becomes p minus 1 over p. When I take the inverse, it's p over p minus 1. What can you deduce about how many primes are there? So this product is infinite. And none of these numbers are infinity. What's the only way this product could be infinite? There's infinitely many primes. There must be infinitely many primes. Therefore, infinitely many primes. With a little bit more work, you can actually use this to estimate how many primes are there up to x. I'll give one more example because somebody mentioned s equals 2. I can't remember, was it Jill? Yes, okay. So I'll stop doing that. So s equals 2, we now have the sum, and it goes from 1 to infinity of 1 over n squared. So I think this is often called the Basel sum. The great Euler figured out its value. Anybody know what this equals? It's a good one. It involves pi.
Is it pi over 90 or is that for the fourth power?
Pi to the 4th over 90 is the 4th power.
45?
Nope. Close. 6. Pi squared over 6.
He's an integer.
Now this is the same as the product over all primes. Now I have 1 minus 1 over p squared. So this will become p squared over p squared minus 1. Now this is a finite number. But now things get interesting. Anybody know what kind of number pi squared over 6 is? It's not an integer. It's irrational. So this is irrational. If there were only finitely many primes, what would this product be? It would be rational. If finitely many primes, it's rational. So because pi squared is irrational, there must be infinitely many primes. A lot more could be said about this. This is the tip of the iceberg. This is one of the most important functions to study. It really understands the primes. And so one of the bits of instruction I got was this was supposed to be intellectually enriching, just give you a sense of where things go. The big theme from today is this local to global principle. Is you start off with small bits of information and you build up a big object from them. And it's only useful if you can then understand the big object. So here, the local pieces of information is the primes. And once we know the primes, we then build this up. And we have this beautiful function over the integers. And we know a lot of things about the integers. And somehow, very similar to the generating function for the Fibonacci's, very similar to the geometric series and differentiating identities, we can now use that to get more stuff. We can get a lot more than just these facts about the primes. These are just two things we could do fairly quickly. So we've got on the order of 5 to 10 minutes left. I want to end with two very strange sequences. Okay, that just means I have big battery, so if this one stops pivoting, I can switch. So how many of you have heard of the 3x plus 1 problem? Okay. The best quote I know about this is it was described as a Soviet conspiracy to slow down American mathematics. Is people would work on it for about a month and then give up in frustration. Another one is mathematics is not yet ready for this problem. And it starts off very innocent seeming. So I define the sequence as follows. an plus 1 equals 3an plus 1 if an is odd, and an over 2 if an is even. Okay. Somebody want to give me a positive integer? 1. All right. 1 is odd, so I go to 4. 4 is even, so I go to 2. 2 is even, so I go to 1, and then I go back to 4. Okay. Somebody want to give me another positive integer? Oh, I'm sorry. No, 1 goes to 4, yes. Somebody want to give me another positive integer? There's a lot of them. 12, okay. So 12 is even, so it goes to 6. 6 is even, so it goes to 3. So doing the 3x plus 1 map. So if your number is odd, multiply by 3 and add 1. If your number is even, divide by 2. So we just saw that if we start off with 1, we go 1 to 4 to 2 to 1. And now we're starting 12 is even, so we go to 6. 6 is even, so we go to 3. 3 is odd, so we go to 10. 10 is even, so we go to 5. 5 is odd, so we go to 16. 16 is even, so we go to 8. 8 is even, so we go to 4. So you want to give me another positive integer. And there's no need to give me 10. Have you seen this problem before?
No,
Yes. That is the one really bad. I'm actually not joking. 27 is a disastrously bad. As an exercise, do this for 27. It will not go on forever, but it will go on for an enormous amount of time, much longer than you would expect. I wouldn't be surprised if that's related because 3s are coming into things.
33? How about that?
We can try 33. So 33 is not that bad. All right, so I multiply by 3, so it's 99, so it becomes 100, right? Then I go down to 50, then to 25, then to 76. And so now this is starting to get to how much we want to do. Okay, so 7 times 3 would be 210 plus 18 is 228, 229.
38.
Oh, this is even. That's right. I get to divide first. That's right. So it's 38. And then I get to divide again is 19. Right. Okay, so now if I multiply by 3, so 20 times 3 is 60, so 58. And then 58 goes to 29.
Yep, 29.
And so,
88.
so the next one was 88. All right, so if it's 88, then this will go to 44. Then it'll go to 22. Then it'll go to 11. then it will go to 34, then it will go to 17, then it will go to 52, then it will go to 26, then it will go to 13, then it will go to 40, then it will go to 20, then it will go to 10. Okay? Anybody want to make a conjecture? Yeah, no matter what number you start with, eventually it will cycle to 421, 421, 421. It turns out that this very innocent looking problem is connected to numerous really good math. And we can't prove this. We can prove things about fractions of numbers that will eventually iterate down to 1, but we can't, I don't think we can even prove close to a positive percent of numbers iterate down to 1. And so what I like about this is, when you're doing sequences and series with your students, you can do the sequence in elementary school. I know I've done it. All you need to do is add and multiply. Now, the numbers get a little bit unpleasant, and 27 is really painful, but it's still just adding and multiplying. And it's a good way to give the kids drills in arithmetic. Can you sniff out the pattern? What if instead of 3an plus 1, what if I did 3an minus 1? What other things can I change in here and still have interesting behavior happen? If I replace the 3 with a 5, what happens? It turns out then with probability 1, things should explode. And we have heuristics to prove why certain things should happen. But this is a sequence where there's an enormous amount of stuff that is still open. I actually wrote a paper on this. You're supposed to spend at least one point in your career thinking about this problem. And so what I was interested in looking at is the distribution of the leading digits of the iterates. And I proved in a certain sense that you have the same digit bias I talked about earlier, where about 30% of the time the digits will be 1, and only about 4.6% of the time the leading digits will be 9. So in terms of if you want to generate fake data to create corporate fraud, or if you want to generate fake data to try to test various things, you can actually do it using the 3x plus 1 problem. You can also do it using the Riemann Zeta-Function in a more involved way. So the last thing I want to do is a new sequence. I cannot tell you the name of the sequence, because if I tell you the name of the sequence, it will give it away. So any questions on 3x plus 1 before we move on to the last item of the day? So I'm going to give you the sequence term by term, and then when you detect the pattern, let me know. Okay, what's next? I'm sorry? Close. 11. 1, 1. 1, 1 is next. Not 1. 1, 1. You were close.
Is it 2, 1 next?
Yes. Okay, you know this one?
1, 2, 1, 1.
Yes. 1, 2, 1, 1.
And then it's 1, 1, 1, 2, 2, 1.
Okay.
I do. I've done it in my geometry class.
Excellent. Extra credit. So what's next? Does somebody who hasn't seen it before today, does anybody know what's next now?
Well, I don't know what's next, but
Oh, I know.
Okay, what's next?
3, 1, 2, 2, 1, 1.
Yes. What's next?
Oh, that was lucky. 1, 3,
1, 3.
1, 1,
1, 1.
2, 2, 2, 1.
So okay, you do. Okay, speak. I've always heard it as look or see. I'll put in speak as well. This is why I can't tell you the name of the sequence when I'm writing it down, because that would give away how you find the next term. You're reading the previous line aloud. I have 1, 1. Now if I read this line, I have 2 1s. I have 1, 2, 1, 1. I have 1, 1, 1, 2, 2 1s. And so this sequence has a lot of incredibly interesting properties. So when you look at the numbers, I'm only using 1, 2s, and 3s so far. Will there ever be a 0? No. Will there ever be a 9? Or what if I have something that has 2 digits? What if I have to write at one point, maybe I have 12 consecutive 2s, but I have to write a 1, 2? So as an exercise, there's never any 4s or higher. Pretty sure it's no 4s. There's definitely no 5s and higher. Pretty sure no 4s are higher. There's some strange coincidences. So you mentioned a strange coincidence earlier today. There's, I think, is uranium 92?
Yes.
Okay. So there are 92 elements. I remember 22 is helium. And John Conway proved the cosmological theorem that from some point onward in every line from that point further down, you always have each of the 92 elements. The original proof, I believe, was lost in his office, and then he and his students came up with another proof. You can ask about what is the rate of growth of this sequence. It turns out that there's a 92 by 92 matrix. And if you've seen eigenvalues, it's the eigenvalue of the largest Jordan block, which is 72 by 72, which governs the growth rate. There's a lot of incredibly interesting properties of this sequence. And this is one of the reasons why I love the lectures that John Conway gives. He takes things that seem completely silly and ends up finding phenomenal good math about this. So he has an article, so this is by Conway, and if you just Google him, it's like something like audioactive decay. It's a really fun article to read. So instead of radioactive decay, it's audio because it's from speaking it out loud. And just when you're doing sequences in series, it's nice to have some fun examples for the students that aren't just the same standard ones you've seen again and again and again, and ones where we don't know all the patterns. So for the 3x plus 1, we have a belief of what's going on. We even have formulas that would predict what's the number of steps we think it will take before you iterate down to 1. So if I give you a number of size, say 10 to the 217, or 10 to the 2017, about how many steps until I iterate down to 1. It turns out that we believe that should be roughly normally distributed, and the mean should be growing with the size of a number in a very well-defined manner. And there's a lot of heuristic models we can do. And so a lot of times it's hard to solve a problem exactly, but we can do maybe a random model. Let's assume that each of these steps happen with equal probability. So half the time you multiply by 3 and add 1, and half the time you divide by 2. If your number is really large, adding 1 doesn't really make much of a difference. So what you can say is, half the time I go from an to 3an, and half the time I go from an to an over 2. And if you consider a random process, you can say, well, what would happen for a typical chain like this? This is now very similar to the whale problem we had, where we now had these random matrices. And we're trying to figure out, well, if we allow some variability in terms of the number of births and whether or not the whales live, what do we think will happen? And by playing the same games over here, we can predict with incredible precision what we think will happen here. The real master for this is somebody named Jeff Ligarius at Michigan. And he has a lot of great papers on the 3x plus 1 problem. Okay, so this is probably a good time to stop. So if there's any questions, people can ask questions and still hopefully beat the traffic. Okay.